Hello students, friends. Today I am going to start module number 2, memories of the subject digital system design using Verilog. Okay, first point in this module is general concepts. Memory. What do you mean by memory? Memory is a storing device. Okay, if you want to store single bit of information, we can store by using flip-flop in the flip-flop. Okay, if you want to store more than one bit of information, we can connect flip-flop together and we can store the information that is in registers. If you want to store more number of information, then we can connect all the registers concurrently. But if the still more information you want to store, then instead of registers we can go for the memory component. That would be the efficient way to store the information. Information is nothing but the binary coded information. Okay, so memory is conceptually an array of storage registers, each of which it has distinct addresses. Okay, now you can see here the address of the memory is varying from 0, 1, 2, 3, 4 up to 2 raised to n minus 1. Okay, so each memory location it has m bits. So each memory location stores m bits. So for n address lines, n are the address lines. Okay, total locations are the 2 raised to n minus 1. So total memory size will be 2 raised to n into m bits. Okay, that is the size of the memory. Okay, so what is the memory size? So memory size, it may be depending upon the locations into number of bits per location. Now this size, it will be varying from kilobits, megabits, gigabits. Then what is meant by kilobits? Kilobits are nothing but 2 raised to 10 are nothing but 1024 number of bits, that is approximately equal to 10 raised to 3 in decimal. Okay, hence it is called as a 1 kilobit memory or 1 kilobits memory. So likewise 2 kilobytes, likewise 1 megabit is equal to 2 raised to 20 is nothing but the 10 raised to 6 are nothing but in decimal. Okay, so therefore 2 raised to 20 is equal to 1048576 bits, approximately is equal to 10 raised to 6, that is 1 megabit. So likewise 2 raised to 30 is equal to approximately 10 raised to 9, that is nothing but gigabits. Okay, so these are the size of the memories. Now let us take one example. We have memory is equal to 32k into 32 bits. What is meant by 32k? 32k are the memory locations and each memory location it will have 32 bits. Okay, then what is the capacity of this memory? Is equal to 32k into 32 bits. 32 into 32 is equal to 1024 kilo. Okay, that is nothing but 1048576. So as we earlier seen, that is equal to 10 raised to 6, that is equal to 1 megabits. Okay, so 32 bits into 32k. What is 32k? 32k are the memory locations. Then how many address lines will require? Let us say 32k is nothing but 2 raised to 5 into 2 raised to 10. 2 raised to 10 is 1k and 2 raised to 5. Okay, so if we collect together 2 raised to 15 you will get. So therefore 2 raised to n are the address lines, that is equal to 15 address lines will require for this given memory of 32k into 32 bit memory. Okay, now in general size of the memory is determined by the application or requirement of the application. So in above example, 1 megabit memory, so we can manage or we can do 1 megabit by using 32K into 32-bit memory. Okay, also we can make the 1 megabit by using 16K into 64-bit memory, or in another way, that is 64K memory locations into 16-bit. So you will get 1 megabits of information. That's why, so memory size will be determined by the application. Okay, it will depend upon the application. It will be having different size, or it will depend upon the application. Okay, next. So we'll see what is the symbol of the memory and what are the basic operations of the memory. So on the left hand side, you can see here, this is the symbol of the memory. So what are the input lines and what are the output lines of this memory? We require memory. So memory will require memory components we have to enable. Whenever you want to do the read and write operation, at that time only we have to activate the memory chip, and hence we will require enable pin. So to write operation, we have to make the write pin must be equal to 1, or if we have to do read operation, we have to make this pin is equal to 0. Okay, so therefore enable pin and write pin are the input pins. Then we require the address lines. So what are the address lines? A0 to AN minus 1. So there are total n address lines. Okay, A0, A1, AN minus 1. So likewise, there are A0 to AN minus 1 are the address lines, and data lines. For each location, how many bits of information you want to store, according to that you will get the data lines, that is data input lines and data output lines. So data input lines are the D in 0 to D in 1 up to D in M minus 1. Okay, so there are M address lines. Likewise, these are the M data lines, data input lines, and M data output lines, D out 0 to D out M minus 1. Okay, so what are the operations we want to perform on the memory? There are two operations we are going to perform on the memory. These are the memory write operation and memory read operation. Whenever you want to do memory write operation, you should enable the memory. So therefore enable is equal to 1, and for write operation we have to make write pin is equal to 1. So whatever the data onto the input lines, that will be stored into the particular location that will be indicated by the address lines. Okay, so that is the write operation. In the write operation we have to make enable is equal to 1, we have to select memory, and write pin is equal to 1. So whatever the data on the input data lines, that will be stored onto the addresses given by the address lines. So next operation is the read operation. In the read operation, we have to again enable the memory, and then we have to make read operation, that is we have to make a write input signal must be equal to 0. So it will assume that it is a read operation, and hence whatever the data shown by the address location, that from that address location that data will be moved on to the output data lines. So data out will be driven with the values given by the address inputs, and in remaining cases we have to make this chip will be idle. So for that enable pin is equal to 0. Okay, so this is about the basic read write operations of the memory. Okay. So then we'll go towards next point. So let us take one example, that is in your book, example number 5.2. It is a audio echo effect unit. on this. So what is this example? Example is a design an audio echo effect unit that operates by delaying samples on an audio signal reached as a stream of 16-bit to the complement binary coded values. The sample rate is 50 kilohertz. Arrival at a new input sample is indicated by control input, that is audio in enable. Audio in enable is a control input. Okay, this is. So this is being 1. Audio in enable is being 1 for the clock cycle in which the sample arises. The unit should indicate availability of an output sample using an output control signal, that is audio out enable. In the same way, the delay time is determined by an 8-bit unsigned input representing the number of milliseconds of the delay. The system clock frequency is 1 MHz. Okay, that is shown here in this waveforms timing diagram. This is system clock frequency. Okay, so sample frequency is given 50 kilohertz, means every 20 microsecond one sample is coming, and that sample is indicated by audio in enable. Okay, so audio input data signal is there and every sample is coming after 20 microsecond. Okay, and this data will be stored into the memory after delay second. What will this delay seconds will be given by the input. Okay, so previously stored data that will be moved out into the next clock cycle, so that is audio out. Okay, and that will be activated by audio out enable. So this is our example. Okay, now how to design data path for the audio echo effect unit or audio delay unit. Okay, so this is the data path. We require memory, then we require counter, we require multiplier, we require subtractor, and we require address selector. Why we require this so many components? We'll see one by one. So memory, what is the size of the memory? We'll see what is the size of the memory. So delay unit is 8-bit input data, and so its rate is equal to 50 kilohertz. Okay, means so maximum delay will be equal to 2 raised to n, that is 2 raised to 8 lines are there. 2 raised to 8 means 2 raised to n means 2 raised to 8 is equal to 256 minus 1 is the total unit delay is in millisecond, that is 255 milliseconds. Okay, so sampling rate is 50 kilohertz, so therefore 50 samples are going to be occur. So maximum delay will be equal to 255 into 50 samples, that is equal to 12750 samples we require to store. In worst case, we require maximum samples will be 12750 samples. Now then, to store this, how many memory size we require? So if we take 2 raised to 13, it will be less than this, and 2 raised to 14, if we take the 2 raised to 14, then you will get required memory size. So 2 raised to 14 is equal to 2 raised to 10 into 2 raised to 4, so that is equal to 2 raised to 16. So therefore 16k 2 raised to 10 into 2 raised to 4, 2 raised to 4 means 16, so 16k into 8-bit 16k memory size or memory locations we require, and each will having 16 bit of information. Therefore 16k into 16 bit is the size of the memory required. Okay, now we required every time we have to increase the memory address by 1. So we require counter, so we require the 14 bit counter, that is the 14 bit counter we required. So to counter we require clock frequency, and that system clock frequency is given in this example is 1 megahertz. Okay, but we have to enable it, we require enable, and according to our requirement we can enable it, so that after every delay second, some delay time second, we can enable it. Okay, then we require output, we have to generate echo effect, so that output will be generated after some time. We have to store the input data, into the memory, and after some time we have to reproduce, and we have to give to the audio system. For that purpose we require delay, and that delay unit, or how much delay, will be given by the input lines multiplied by 50. So delayed information or delayed address lines will be given by this. So current address minus delayed address, you will get the required memory location. So to do write operation, to store the memory, so we can use this address directly from the counter, and to recall or to do the read operation we require the subtractor output. Hence to select these two addresses we require multiplexer. Now you will get, so we require memory, we require counter to generate addresses, we require delayed unit, we require the subtractor. Okay, and then we require multiplexer to select the addresses. Okay, so this is your audio echo effect unit. Okay, then how to generate the control signal? So control signals, which are the control signals required? You can see in the example, or you can see in this diagram. We require the address select, audio in, audio, memory in, memory write. Okay, counter enable. These control signals we require. Now see here, so these are the control signals. Audio in enable is the input. Okay, according to that we are going to move. So address select, memory enable, memory write, counter enable, audio out enable. These are the control signals, so that control section has to generate. So now our operation has two operations, that is we have to do, one is the write operation and one is the read operation. So when we are going to do, when input signal is ready and input signal is given by the audio in enable is equal to 1. If audio in enable is equal to 0, we have to do in idle state. Okay, so that is do nothing. Okay, that is idle state, and that is shown here in the step 1. Audio in enable input is equal to 0, then we have to remain into idle state, nothing to do here. Okay, if audio in enable is equal to 1, then we have to go for the step 2, and what is the current? We have to do the write operation. What is the write operation? We require the address select is equal to 0, that is counter address we have to generate, and we have to activate memory, and this is memory activated enable, and we have to do write operations. So these are the zeros, so these two signals must be equal to 0. Then next operation will be write operation, and after that we have to go for step 1. Next operation is the read operation. Okay, so read operation, address select is equal to 1, that is we have to generate the subtractor address, and this is subtractor address. So memory we have to enable, we have to activate the memory, and then we have to do read operation, it must be equal to 0. Then counter we have to increase it by 1. Okay, and we have to generate audio out enable signal. So this is about the audio echo effect unit. Okay, that's we want to design. Okay, so today we'll stop here.